Good evening, everyone. Thank you for joining us for the second session of the data analytics sessions. So today we'll be dealing with machine learning, and we are the sessions would be led by Professor Najam Hassan as well as Priya Hassan, as well as Professor Peng. I don't know if he'll join, but he did the first session of he was part of the first session. So I probably think he'll also join the session as well, right? So yeah, I think please note that this session is also recorded for and is accessible on our YouTube page. So Professor Najam, over to you. I don't know. Prof, sorry, can you hear me? Oh,
Hey, Lebo, I can hear Prof.
I think maybe there might be a problem with
A
their
glitch.
connection.
Yeah, maybe it's frozen. Yeah. Okay.
It's fine. I'll text Priya just quickly, and then I'm sure they can get it sorted out.
Okay.
You having a problem with the audio? You can't hear?
Yes,
Debo.
yes, we couldn't hear Prof. But
Now
we
you
can
can
hear you.
hear?
Yes, we can hear you clearly, but we still can't hear.
Can you hear me?
Yes, perfect.
Okay, great.
I think we are hearing him from Priya's microphone, not
Microphone. Could be,
not
could
that
be.
of Prof. Yes.
So Prof, we could only hear you from Priya's microphone. There seems to be a problem with yours.
Hello, are you still having a problem hearing him?
Yes, but we can. You're very audible. It's just that we can't hear Prof at all.
Okay, then I'll
Can
keep
you?
my mic open. Is that okay?
Yeah,
I'm
yes.
keeping my mic open and let him speak. Okay.
Perfect. That works.
Yeah.
Can you hear now?
Yes, yes, we can.
So, hello everyone. This is Hassan, Najam Hassan, and I'll be giving you a very short introduction to machine learning, and then we'll run through a certain uh, Jupyter files which we have shared with you, or will be sharing with you, where we'll see some examples from astronomy and how machine learning is used in that. So, the outline of this short presentation is we'll look at what machine learning is, the types of learning, the type of data representations we have, clustering and k-means algorithms, then dimension reduction and principal component analysis, and with some examples of astronomy all through. So machine learning is used in astronomy in a variety of ways and for a variety of things, but in these few sessions we'll be touching upon some very essential ones which are used most of the time. So what is machine learning? As we have discussed many times and reiterated that we are living in an age of big data, where there's petabytes, exabytes of data which is being collected in all walks of life and also so in astronomy. There are large surveys where tremendous amount of data is flowing in, and the rate at which it's been flowing in and the rate at which you have to analyze has also gone up. The speeds have gone up tremendously from gigahertz, teraflops, and so on to very high speed networks. And we require new algorithms, new methods to analyze this complex data which is flowing in. All these three aspects help create the current boom in machine learning. So what is machine learning? As Arthur Samuel says, machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. So what do we mean by that? Basically, it implies that like in earlier times, a few decades back, we would have data and we would have programming languages which we had to write programs to sift through this data and analyze it and so on. But machine learning is a technique where you don't have to explicitly program, but the machines are trained to understand the data and to analyze and give outputs. We'll have a look at that. For example, we can train machines to understand what a spiral galaxy is. We show them different images of the spiral galaxy and train the machines, or we can give a set of different elliptical galaxies with different inclination angles, orientation, sizes, colors, and train the machines to understand what an elliptical galaxy is. And then through a survey where we don't know the morphological types of these galaxies, which have to be ascertained, we use machines to do that. So the machines compare these images and bins them into different categories. So work which had to be done over a lot of time can get done very fast using computers, because the capacity of computers to sift through terabytes of data of millions of galaxy images which have been collected in a very short time. So it's something like even for human beings, for a child, we teach a child that this is an apple and a red roundish thing, and the child looks at apples and says apples, and we say, yeah, you are right, you are correct. But there are times when the child may pick up a tomato which is red and round and would say this is an apple, and then you would say no, this is not an apple, it's a tomato, and so on. So you train human beings, we get trained right from our childhood to understand, get a final image of that object, and then when you see the real object, you realize that apples can be green as well as yellow as well as red, and you understand what the abstract apple is and you can bin them. So the same thing goes with astronomy images or astronomy spectra, where earlier humans had to look at different spectra and classify that spectra of stars into O stars, B stars, G, and so on. And instead of human experts, now we have machines which are trained to understand different spectra. They are trained on these sets, and then the machine is given a series of various spectra, and it understands and bins them into different categories. So the work gets tremendously reduced and solved. So once you have trained them, the machines can identify objects from astronomical images and detect galaxies in the surveyed images. They can classify those galaxies into lenticulars, ellipticals, spirals, irregulars, and so on, and can distinguish elliptical galaxies from lenticulars or spirals or stars. You can differentiate an image of a star from a galaxy, and so on and so forth. So the way it's done is you have data, where we see this block here with a D here. Then you have a predictor function which we define. And when you feed the data which you have obtained in this function, it predicts, it says whether the spectra which you have fed is that of a G-type star or O star or so on. And then we make an assessment of the error. If the errors are large, then you tweak the predictor function, change it, alter it, so that it gives you a better result, and you do it till the time the errors or the losses or the fits are good, errors are least, and which gives you a good predictor function, and then that helps us to analyze data very easily, very efficiently. There are different types of learning. You have supervised learning and unsupervised learning. The term itself indicates what they mean. In supervised learning, when we are training the machine, we train it. We have a list of objects which we know are specifically, say, spiral. In case of galaxies, we know specifically that these are spirals or these are lenticulars or ellipticals, and we have this labeled data inputted onto pairs, and the computer is trained on that, and then you use that for classification and regression. In the unsupervised one, we have unlabeled data. The data which we feed in doesn't have these labels. It doesn't specify that a specific galaxy is a spiral, lenticular or not, but the machine itself tries to make clusters, make groups of objects which are similar, right? For example, you have spectra of various stars or clusters, and then it looks at the color of those stars and measures the temperature, and if you have information about its mass, reddening, various things with which it tries to find out groups and starts binning them. It says this is a star, this is a galaxy, this is a quasar, and so on. So the machine itself learns. We don't have, so you have data which is without labels, and this is unsupervised learning. Usually includes clustering and dimensional reduction. So dimensional reduction word itself indicates that when you have data with many parameters, and not all may be a reason for its certain property. So we try to find out those specific parameters which are essential to categorize that object. So for example, I may have a table with the first column having names of the objects, second column its right ascension, third declination, then it may have its magnitude and a certain filter R, G, B, U, and so on. We may have parallaxes, we may have extinction coefficients, metallicity, and so on. So there is tremendous amount of things, and we want to find out whether that object is a quasar or it's a star or what object. So you realize that you don't require to know its position. RA and Deca are irrelevant to decide that. So you realize that U minus G, the color is more important, and so you find out those components, those parameters which are essential for defining a certain object in one category or the other. So you reduce the dimension. Instead of a 20-dimensional space, you boil it down to 3 or 4 or 5 dimensions, and then it becomes easier to analyze the whole thing. So we'll be seeing examples of this as we proceed. A non-astronomical example for what machine learning does is here. We have, say, Indo-Arabic numbers 0, 1, 2, 3, 4, and 9. And we have these Roman numerals 1, 2, 3, 4, 5, 6, 7. And we train that 1 is this and 2 is so and so, and you train it, and then you test it out. You give a series of numbers and you make a guess. Like for example, the first one I say it's Indo-Arabic 1, and the label given to that is also that, so it's going right. Second one, the label is Roman and we have also guessed it's Roman, and same with the third. But with the fourth one, it's a Roman number, the label is Roman, but the machine or it guesses to be Indo-Arabic, it has gone wrong there. And the last one again is going fine. So we look at the accuracy of how we are retrieving, how the machine is trying to, your guess, by your guess I mean here, what the machine after having learned is trying to guess what these things are. So these are the machine guesses, and we see that 4 out of 5 are correct, so the accuracy is about 80%. We have yet another kind of learning called reinforcement learning. And in reinforcement learning, the algorithm explores the data and it tries to reach the right analysis understanding by trial and error. It tries to understand what it is and looks at the errors in it and tries to correct it and reinforces. It's something similar with human mind also does. We may make mistakes in guessing a certain thing. A child may make a mistake between a stool and a table, and then you correct it and say, no, this is not a table, but it's a stool. And you keep, so from the errors, the mistakes you make, you correct your knowledge system and you do it. So this is the reinforcement learning. And in astronomy too, it is of much use, where you may have robotic telescopes which are trained to look at some objects, and by trial and error, it finds out how best to do it. It may take into account observation time for how long it has to observe to improve the quality, or it can be based on the symbol to noise ratio to decide what to object when and so on, or in the scientific priority list, it learns what are the objects which are essential to observe at that moment. Like there could be a transient which is coming, a supernova. So the robotic telescope is trained that some transient object is a more important one for it to hunt out. So by trial and error, it learns how to take observations on its own. And the data representation also comes in a variety of types. You have categorical data, ordinal, and numeric. Categorical, for example, you have galaxy types, we have elliptical, spirals, and irregulars. And usually we encode these as numbers, and these are mutually exclusive. If a galaxy is elliptical, then it is not spiral. If it is a spiral, it is not irregular. So they are all mutually disjoint sets. And the labels are given to that. You assign labels 0, 1, 2, and so on. And these are encoded in numbers, but you cannot do any arithmetic calculations with that. So if I'm giving category 0 to all ellipticals and 1 to spirals and 2 to irregulars, there is no question of adding 1 plus 2, and you don't do arithmetic with that. These are just labels, and for convenience we are giving these numerical values. Ordinal data, it could be something like quality. For example, the seeing of a place is poor, fair, good, or excellent. So you assign these ordinal categories. And the comparisons are meaningful here, right? So you can say it's how poor it is, how good, or really how good it is, excellent, and so on. And then you have these numeric ones where you have numbers. You may have integers or real numbers which give these values. And obviously for these numeric data, you can do all mathematical computations, addition, division, multiplication, and various things. And for example, these numeric data will give the redshifts of an object, the flux coming from a certain object, from a star or a galaxy, what is the magnitude, wavelength. These are all numbers, so this is numeric data. And here the mathematical operations are meaningful, because if you have magnitude in red and in blue, then R minus B, and you can do subtractions and so on and get the color index and so on. So labels in multi-class classification, for example, you have different classes: elliptical, spirals, irregular, and star. We give numeric labels of 0, 1, 2, 3, and so on, and you give you get encoded as 0, 1, 0, 0, 0, 1, 0, 0, and so on, so that the computations and machines become extremely convenient and so on. Other than that, we have time series data, we have say stellar spectra or so on, where you have with wavelength you have the flux there, or across time you have how the intensity is changing. So you have spectral data and so on. Okay. So it's very important to define the task for which your machine learning is being used for, right? We have to get the data, and we have to choose the right representation to denote this data. Then we have to explore the data using statistics and visualization. This has been covered in our previous sessions. We have learned how to use pandas and NumPy and stats packages, and Matplotlib, Seaborn for visualization. So you explore the data, then you prepare the data, you normalize it or get it in a form which you require. If you have, say, different categories, you give numeric values for the convenience and so on. Then we have to choose the correct model and train the data machines, then evaluate it, check how good your recovery is, how accurate your system is, and then evaluate on the test sets. And right, so generally what you do is if you have data where you exactly know the objects and you know exactly what categories they belong to, right? So you use it as a training set, and very often you use a certain part of this set to train, and you use the other set which you have not used, where you are very confident about its knowledge. You try to evaluate your algorithm and see how much it retrieves and see how much of data it's recovering, right? So you evaluate the test sets, then you launch it and monitor and you maintain it. Okay, so this is what goes into machine learning. So computational reproducibility means obtaining consistent results using the same input data, using methods and analysis conditions. Keeping all this the same, you have to keep getting the same data reproducibility. And the sources of stochastic are the random initializations. There can be shuffled data sets, there can be changes in the software framework, there can be noisy model components and so on. And the tools which we often use are these version control data set variations and saved hyperparameters and model sharing and experimental tracking. Coming to clustering, you have the set of data, and then k-mean clustering especially, you define the number of clusters you want to break the whole data into it. So randomly you say you want k clusters. In the example on the right, we have chosen 3. So the data set we are looking for 3 clusters, and we put 3, and it randomly places a centroid, and it calculates the distance of each object from the centroid, and assigns each point the closest, the distances which it calculates. It assigns that cluster point to a specific cluster if the distance to it is the minimum, to that cluster, to that centroid where the distance is least, it assigns that object to that. Then you calculate the mean of these, and you create the new centroid of this group which we have created, and again it goes in an iterative process. It repeats till the time it breaks up into these 3 different categories. Okay, so this is an example how it keeps hunting. In the first frame we have 3 centroids arbitrarily chosen, then it moves the centroid of one towards one of it and the other, and then it keeps hunting. Finally it breaks up into the thing. In dimensional reduction, which I've already mentioned, you have large data sets, and you have correlated variables and uncorrelated ones, and the idea is to find out what are the variables which are correlated, which are important to study to understand a certain phenomena or certain nature of that object. PCA is a good technique which is called the principal component analysis, which tries to find the important principal components of the whole data. So you decide how many principal components you need. So whether you, for example, in this we are looking at data with which you are looking at two principal components, and you see how they are scattered. One direction, there are two orthogonal sets, one where the dispersion is the least and where it's maximum. So the maximum dispersion gives you the maximum variability of it, and hence you find out, and then you can study these objects in terms of these principal components. You can neglect all other parameters, all other components, and just focus your attention only these things. So these are essentially important, especially when we have very large databases with tremendous amount of data. These PCA and these algorithms all have their nuances and caveats. There are times when they are not very effective or they can fail. And for example, PCA works best when the important structure is linear, and it can fail very badly when you have, say, some kind of a circular or a periodic, non-linear distribution. For example, if the data is arranged like that, then you cannot find the radial distance or the azimuthal angle theta, which will make any difference at all. You'll get the same values all the through. So the clusters are separated by shape rather than the variance. So as a summary, machine learning learns patterns from data. Supervised learning uses labeled examples. Unsupervised learning finds structures without labels. Data representation is central to this performance. K-means group similar objects. PCA reduces high dimensional data such as stellar spectra and so on. We'll see examples in the Jupyter file, which I'm going to run through soon. And astronomy provides rich data sets for modern machine learning methods. So thank you. I'll stop with this and come to the second aspect of, we will look at okay. Not this. Can you see this?
Not yet. It's not yet come on the screen. It's still that thank you slide. Just see, this is what is coming.
Yeah, okay.
Now it's coming.
So we'll be sharing this Jupyter file, which is a short one, which kind of again goes through the things which I've discussed, which essentially says that astronomy has entered the era of big data, and there are large surveys like Zwicky Transient Facility, and there are Rubin's Observatory Legacy Survey for Space and Time, LSST, and so on, where tremendous amount of data is flowing in, and the sheer volume and complexity of data has surpassed our ability to analyze it manually, and machine learning offers a powerful set of computational tools to address these challenges. So at its core, machine learning is a science of teaching computers to learn patterns and make decisions from data without being explicitly programmed for every task. Instead of writing rules, we provide data and let algorithms learn the rules itself. Right? This is the heart of machine learning. And here I've discussed again what supervised learning is and where is it used. Right? So supervised learning, the analogy you have is you teach a child to identify animals by showing them pictures with a label. This is a cat, this is a dog, and after seeing enough examples, the child can identify new picture of cats and dogs and says this is a cat or a dog, right? Extending this analogy to astronomy, we can teach or train the machine to identify galaxy morphology by showing in these sets. We show and say this is elliptical, this is spiral, this is lenticular, this is irregular, of different types of galaxies with each with a label, right? This is elliptical, this is a spiral, and so on. And after training with enough examples, the machine can identify new images and bin them in different categories into any of these four. Okay. Or further, it can say it is not a galaxy, it's a quasar, it's a star, or so on. So this is supervised learning. And supervised learning, as to reiterate, the goal is to predict a discrete category. The output is a class labeling. So the question is, what kind of an object is this? And this is a star, a galaxy, or a quasar, or this is elliptical, or a spiral, or a lenticular galaxy, right? Regression, the goal is to predict a continuous numerical value, which gives the property of the dependence. And for example, what is the galaxy's redshift, what is the star's temperature, and so on. So we use these things in classification. So when you have categories, you use this classification, and we use regression when you have numeric data, so that you can bin galaxies in terms of their redshifts or stars in terms of their temperatures and so on. Unsupervised learning, that algorithm works with data that has no labels. The goal is to find hidden structures, patterns, or grouping within the data itself. The analogy is you give a child a box of mixed Lego bricks and ask them to sort them into piles without any prior instruction. Now it's up to the child to group them in whichever way they like. They might group the bricks by color. They may put all red blocks together, all white blocks together, and so on, or by the shape, the big rectangular pieces all together, or the squared pieces, or one with two, right? So it's up to the child, and the child groups them, tries to understand the structure in it, and does it. Something similar is done even with machines. We have a survey of galaxies of all morphological types, and we want to sort them into bins. Without prior instructions, we might group the galaxies by color or by, right? So we don't tell the machine that this is a spiral, this is lenticular, this is elliptical, but the machine itself looks at the data and tries to analyze it or group them into different categories by a certain property which it finds is important for grouping. So the algorithm discovers the structure on its own, and unsupervised learning is often used for clustering and for dimension reduction and for anomaly detection. So, okay, so these are the examples. Are there any natural groups in my data? You have data collected from some, say, a Gaia dataset. You find groups of stars with similar motion in the Gaia dataset, which might be a star cluster. Group galaxies based on their observational properties, right? The dimension reduction, the goal is to simplify the data by reducing the number of input features while retaining the most important information. So the question is, can I simplify my data without losing key information? Take 100 different measurements of galaxies and find the 3 most important underlying variables that describe most of the variation, right? And it is used also in anomaly detection. The goal is to identify data points that are significantly different from rest of the data set. So you have the data set which you see some outliers, you see objects, they are very different from all the others there. And then these can become an interesting objects to study or to analyze and to understand. So yeah, so This here's a summary, and this will be shared with you. Now we'll go to the next Jupyter Notebook, and here we shall be using some astronomy data, but this is generated data. We'll be generating the data very similar to the kind of data we'll get from surveys. The reason for doing this in this session is the data is much simpler and the running time would be shorter, so we will not waste time into that. But this data is very similar to the kind of data which you can download from archives and large surveys. So as we always do, we import all the libraries. So I'm running this notebook. Import NumPy as NP, yeah. Import pandas as PD. Import matplotlib.pyplot as PLT. This you have seen in earlier sessions too. NumPy, pandas, matplotlib we have used for handling data and data frames, tables, so on, and doing mathematical computations, plotting, seeing dependence of one column with another, and so on. What we shall see here beyond what we have done earlier are looking at this scikit-learn one, where we are using from model selection of scikit-learn, we are importing train test split. Then from pre-processing, we are using this standard scalar, and we are using this random forest classifier and random forest regressor for classification and regression analysis to be doing, and we'll be importing k-means for clustering, and we'll import PCA for principal component analysis. And then we'll import this accuracy score, classification report, and mean squared errors. This is essentially to see how accurate our algorithms are working, and look at the results, the reports which the classification gives, to see these reports and so on. So we'll go through these to term by term. What do we mean by train test split, and what does standard scalar? So we import this train test split from sklearn.module model selection because it handles a common machine learning preparation step. It is used to split the dataset into training and testing paths. So in this notebook, you see this command. As we see below, we'll run it, and yeah. So this is to you split the data. Then in the notebook, the model learns from the training data, and this helps us check whether the model can make good predictions on new unseen data instead of only memorizing the original data set. We import the standard scalar from pre-processing because it is used to standardize the numerical values so that they can have similar scales. You may have a table where, which we shall see soon, if you are just looking at the color, G minus U or so on, the values are 0.12, 0.37, 0.25, below 1. But if you look at, say, the redshift there, or you see the parallax, the numbers are going into 14, 13, 12, so on. So when you try to analyze data which are of different sizes, some are very large values, some are very small, then the PCA and regression, and they start giving more value to the larger numbers, which may not necessarily imply that they are important. So you re-standardize them, you normalize the data. So you will see that the data set which we are going to create here, the values, yeah, and then you rescale it in such a way that the mean is approximately around 0, and the standard deviation of all the columns are standard deviation is 1, and then it becomes easy for us to do. So now here we are creating astronomy photometry data set. We are simulating SDSS, Sloan Digital Sky Survey like database with 5 photometric bands U, G, R, I, and Z, and the objects are labeled as star, galaxy, or quasar. Right, so this is where I do it, and what this has done is it has created, as you see, 1500. Your n is 1500, and we are randomly creating 1500 data entries where the star, galaxy, and quasars are randomly scattered in each row. The size you see is n here. N is 1500, and you give the p-value as 0.4. So at what frequency the stars, galaxies, and quasar come, I'm giving it here 0.4, 0.4, and 0.2. And I'm creating here different objects U, G, R, I, Z for the star, similarly for galaxy and the others. And we are storing it into a data frame DF, and this is what the table looks like. These are the first 5 your df.head. We are looking at the first 5 rows. They are essentially 1500 such entries, and you will see what the U magnitude is, what G magnitude, what I, R magnitudes are, and the different redshifts which we have randomly created, and the different classes. They are star, quasar, galaxy, galaxy, star, and so on. So these are randomly scattered there. And these other 4 columns, U underscore G, G underscore R, R, these are the U minus G. So your value which you have U magnitude in U band and magnitude in G band, we are subtracting it and putting it here. And similarly for the second row, third row, and so on. So we have 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. 11 dimensional table, and you have 1500 such columns. Okay, so we look at the color diagram and we are plotting it. So we are grouping by class, and you see they are grouped here. And what do we see here? The galaxies are all in blue. They are sitting in U minus G, G minus R, the color diagram. The galaxies all appear to be sitting in one region, while the quasars are sitting, these orange dots are quasar, and the star, right? So indicating that the temperature, the color diagram breaks them into different regions where you can you identify whether this is a star or a galaxy. You may see certain regions which there is an overlap. There are certain objects which are stars, but they are occupying the region in this color space where the galaxies are sitting, and also in the quasar ones. Okay. So in the supervised classification, this was just the visualization of the whole thing, and now we'll run the supervised classification. We train on the set which we have created. From this table, we are training our sample, and it is done by this command here. Train. These are the labels which we are giving: xtrain, xtest, ytrain, ytest, and we are using the xtrain test split which we discussed above. So it's going to break up our data into training sets and test sets, and we are specifying the test size to be 0.25. So we are using 75% of the data points to train, and then we will try to retrieve. We want to check overall again on these 100% data set, and we test it on the 25% of these points and see what kind of results it gives. So I run that, and and again you will see what we are using the random forest classifier to classify them into using random forest algorithm to classify them, and n estimated 200 uses. We'll discuss this a little soon. We'll breaks up into 200 different sets, and the random state 42. This is for the continuity, so that when you run it again, the random numbers, it uses the seed 42 to do that, so that when you repeat the whole thing, you should get the uniformity of results and the same values. The clf.predict, it tells you what is its prediction thing, and it gives you the accuracy score by this command, accuracy score of X test and Y predicted, right? What is tested and the prediction, how good they are, and then classification report, right? So accuracy it has given us 0.9866, and what it's saying is in 90% of time this is giving a right prediction, right assessment of this thing, and in for galaxies the precision is 1, perfect 1. Quasars, they are small errors 0.99, and star 0.97, right? And this is the report which is generated. And looking at the explanation of these commands which I've run, I've given it here. So this code trains and evaluates machine learning models that predicts the astronomical objects, whether it's a star, galaxy, or quasar. The features which we have are U, G, R, I, Z, U, G, and these colors, right? Those 11 columns, feature space which we're looking at in this table. So this is defined in the features. This is the features, and this creates a list of input columns, and these are the features that model will use to make predictions. U, G, R, I, and Z are the brightness or magnitude values in different astronomical filters, and like you all know, U, G, R, G, and all are color indices, implying the difference between the magnitudes in U and G band, and this helps us describe the object's color or the temperature. So we have defined X as DF features, and this selects those feature columns from the data frame DF, so that X contains the input data, and Y, small y from DF keeps the classes, and this selection is targeted towards the Y one, right? So when we are classifying them, we are interested in grouping them in stars, galaxies, or quasars. So, and when we are running this command, xtrain, ytrain, z, these are the variable names, and xtrain split test size is 0.25. That is 25% of data is reserved for testing. 75 years is this for training, right? So the data splits the data into training and testing sets. The xtrain and ytrains are used to train the models. Xtest and ytest are used to test the models. And the test size means 25% of data is kept for testing and 75 is used for training. And the random state 42 makes the split reproducible. So you get the same result every time you run the code. And the stratify, we are using Y list to keep the same proportion of stars, galaxies, and quasars in both the training and testing sets. The CLF variable name which we have defined is the random forest classifier output will be stored in CLF, and n estimator 200 and random seed 42. This creates a random forest classifier. A random forest is a collection of many decision trees. Each tree makes a prediction and the forest combines their votes. So when we specify n estimator as 200, means that the model will use 200 decision trees, right? And then clf.fit will fit for the trained data. This training trains the model using the training sets, and clf.predict will predict whether uh, uh, what those objects are, and we stores it in ypredict, right? So we have y and ypredict, and ypredict is what our machine is predicting it to be, and then you will print the accuracy scores and the report and so on. Okay, so so when we can run that, and we see that this is what it is, and this is the accuracy, and again you can plot this y predicted against the actual ones and see how well we have made these clusters, right? So you can run this separately again and just write a small block where with y predict you can from the y predictive list you can plot u minus g and g minus r and see how those objects get classified. Okay, so this is set for, and looking at the feature importance, this code tells us which is the most important feature which is grouping them, and the feature score shows that u minus g, this is the maximum value, right? This is most important for it. Then the u magnitude and g minus r, they come second, third in number, then z and so on. And the least important is this, right? So this is just a histogram plotted horizontally, and it is because we have run this command with bar h. If I have bar and run it, then you would have got it like that. But in this analysis, we are not looking at the histogram, the classical way of looking at histogram. Rather, we want to see which is most important feature in the star galaxy and quasar classification, right? So regression estimating the galaxy redshifts, we use the random forest regressor, and again n estimator is 200 and random state is 42, and we run it on the x train and y train sets, and we predict using reg.predict. We predict it, calculate the root mean square error, and calculate what is the error in it, and we are plotting it here, and what we see here is the photometric redshift. Our root mean square error is 0.295 and so on. So, and it's very important to know that the prediction which it is giving, the kind of regression line which is giving, how accurate, how good it is. And it is very important to understand that. And for this, I have given an explanation here. The first few lines tell us what this random forest regressor does. And yeah, basically, the random forest regressor is made of many decision trees. Each tree predicts a number, and the forest combines the predictions, usually by averaging them. And the estimator 200 means the forest uses 200 decision trees, and the random state 42 makes the results reproducible so that you can keep getting the same number. So important thing when we want to look at the root mean square error, whether the question is whether this error which we have got, is it small or large? And one has to realize that the root mean square error can range from 0 to infinity. It can never be negative. 0 indicates the prediction is perfect, 100%, but very often, in fact, in all the cases, you will see that getting a root mean square error as 0 is is pretty much impossible. You get some errors because there are errors due to observations errors, truncation errors, and there are various errors, instrumental errors. So, and predictions also cannot be 100% one. And the last root mean square means was bad predictions. And one you have to check whether the prediction is good or not. We rescale. We look at the maximum y-test value, minimum, and the maximum value, and you subtract the two, and the root mean square you divide it by this value. Okay, so this is giving you what the minimum value of y-test is and what maximum is, and what root mean square is, and then I normalize it and I run it, I get 0.206. So basically it's saying about 20.6, the errors are about 20.6. So around 80% of the time it's doing a good job. And you can also check it with the mean redshift. The mean redshift value is 0.49, and with that, when you divide 0.295, that number, with 0.46, you get 70% error. So in the mean one, you are seeing that 30% of the time it's going bad, 70% this regression is giving well. So the data which we have created by this algorithm is giving 80% accurate ones, and so on. So k-mean clustering, this block of code, this is an example where you don't have label data. We ignore the y1. We don't use the column where your star, galaxy, or quasar is listed there. Star is listed there, and we run it, and we are using this scalar fit transform basically to normalize the data, and we are fitting k-means clustering for clustered numbers to be 3. We are saying to break the whole data set into 3 different clusters, and the random state is 42, and maximum iteration we specify as 100. Okay, and it will do 100 iterations, but I have also included a line here where all close. So if the iteration, the centers and the new centers are not varying much, then it breaks out of the loop before it does 100 iterations. And when you run this, you see that it is distributing this data into 3 groups. So we don't know what are galaxies, this, that, but it has found that this data is broken up into these 3 categories. And it is exactly very similar to what our clustering algorithms also did. And we can realize that these are, and once you start looking, you will realize these are galaxies, these are stars, and these are quasars, right? So, and then this is the table which gives you how many galaxies are there, how many quasars, different category ones, these things are. So this block explains you what the standard scalar does, basically rescaling of normalizing the data, and we use the NumPy k-means array to create a random number of generators with fixed seeds so that they are repeatable, and it finds randomly 3 centroids and starts calculating the distance of each from it, and the shortest distance a point has to a centroid, it moves it into that cluster. Then for that cluster, it calculates the mean, moves the centroid to that location, again recalculates the distances of stars from this, and again puts them in different categories, and it does repeatedly till the time it reaches 100 iterations or reaches the stage where the values are not varying too much. So similarly, in the next few minutes, I'll just look at the synthetic stellar spectra, and this is with the PCA, and we are constructing artificial data here, stellar spectra, and we have hot stars is given here, sun-like stars spectra is given here, and this is the cool one. This is what I've generated in this block. Essentially, this is what the spectra looks like, and in the right-hand side, you will see the hot stars, the sun, and the colder star spectra. This is what they look like, and we are using principal component analysis to analyze this data, and what PCA does is we have specified here that the PCA the n component should be 2 here. You can specify how many components to start off with, and PCA dot fit transform spectra scale, it transforms the data into the data into a form which it uses for its analysis, and it breaks them into hot, sun-like, and cool stars and arranges them. And here we are seeing a graphical representation of how it has seen that whole data and breaking up the data into 3 specific groups, and it shows the variance ratios and gives what is the explained variance of the whole thing. So the standard, the scalar, standard scalar standardizes the spectra data so that each wavelength features has a similar scale. Then PCA component 2 creates PCA models with reduced data of 2 principal components, right? So it tries to find out basically 2 components which are most essential for that. And you would see that U minus V and U are the 2 principal components which get the maximum out of the data. And on the basis of these 2 principal components which it has found, it tries to break up the data into this. And the interpretation of this, what we have done, is given here. And see, it is showing that it is breaking up into basically 2 different components, wavelength and the component weight. And the PCA1 gives you a certain profile, and the PCA2 gives these. You have certain exercises for you to try, and with this I will stop. Thank you.
What was the name that this Peng logged in the morning? I can't find him. I'm asking him, are you online? What did he log in as?
You speak there.
I'm asking, but I don't know. Peng, are you there? Hello? Mr. Peng, are you there? Hello?
I can hear you, Priya. I'm not sure it's here.
Yeah, because I can't, I don't see him.
Yeah, he's not here. So I think we probably will end it here because he presented in the morning. I guess maybe the time is late for him to join.
No, if you want, I can continue. I have something, I can do it. Do you
Okay,
want-
then in that case, you can go ahead, Priya.
Yeah, okay.
Okay.
So then I'll go ahead.
And then we can take the questions later.
Yeah, and we will take questions also. There are some
yes.
questions already there. I see Kiran says, yeah, okay, is Gaia-metric data, Gaia is photometric data, yes. Okay, and okay. I'll share something, but I mean, it was not exactly planned, but it's fine, I'll do that. Yeah, okay.
If you want to stop a little earlier and
Yeah.
ending up a gas, I can work on something
Okay,
and do it.
yeah.
Something more.
So I hope you all can see my first slide. Yeah, all's fine, right?
Yes.
Yeah, and you can hear me also fine.
Yes.
Okay, okay, very good. So what I'm going to do is, as a part of the machine learning part, I will talk about some work which we actually did in machine learning. This is with one of my PhD students, or rather 2 PhD students, and this is work that we did. One of the students has already got his PhD. The other one, that is this boy, Mudassir, has already got his PhD. While this guy, we are in the process of submitting his thesis. So this would be just a good example of describing what is the kind of solid work that one can do with machine learning. Okay. So basically, what you've been seeing is that now with the paradigm where we have so much of data in astronomy, right? Earlier, what happened when we did astronomy, it was you had lesser data and we did what was called hypothesis driven science. In the sense, you observed something, you had some hypothesis or some theory to explain it, right? You did an experiment, right? You did some data analysis. For example, let's talk about Hubble's law, right? So for example, you observe the Doppler shifts of galaxies, you do that experiment, you analyze the data, you plot V, that is velocity of the galaxy, versus the distance to the galaxy, right? And what Hubble got was he got a straight line fit where he got V is equal to h into d, where h was called Hubble's constant, right? So basically what he did is that the velocity of the galaxy was directly proportional to its distance, right? And then you say, okay, this explains what you understand it, and what do you say? This says that the universe is expanding, right? Because you can see that galaxies, as their distance from us increases, right, the velocity seems to increase. So it's as though galaxies are kind of moving away from us, right? As the distance increases, their velocity increases. So this is what we call hypothesis driven science, right? Where you do an experiment, you get some results, you use your results to interpret it and actually come to the conclusion that the universe is expanding, for example, right? Now, in today's time where we have so much of data, right, we have data rich science. In this case now what happens is, let's assume now you have data of velocities of galaxies, right? So you actually measure you have the data for velocities of galaxies, you have data about the distance to those galaxies, and then you try to explore the data, right? You look at this data, which has velocity, distance, many other parameters, and then you try to get a pattern, right? You try to explore the data, study the data, and get a pattern in the data, right? And then probably you would again come to Hubble's law because you discover that V is equal to h naught into d, right? And that would give you your discovery that Hubble's law takes place, right? So here what happens is, in data-driven science, you actually have data sets, you explore data, your data helps you to see a pattern, right? Based on that, you put a hypothesis that why should these galaxies have velocities proportional to their distance. So then you put in the understanding that you have an expanding universe, right? So in today's time, what happens is, since we have so much of data, we have different parameters for objects, we can actually use this data to look for patterns, right? Look for some patterns in the data. And then based on that, we actually build a hypothesis, right? So you first have the data, then you build your hypothesis, then you do your data analysis and you do your understanding, right? So these two things gets reversed. Instead of doing your experiment, you do your data set right in the beginning and then you get your theory. Earlier, you first had your theory, then you do your experiment, right? So in this way, what people are doing is that now they're actually discovering different ways of understanding data, right? So that's exactly what we are going to talk about, that now when you have such a lot of astronomical data, right, you have, say, a catalog of galaxies or catalog of stars, various things about them, different parameters, and then you want to look for trends in the data, right? You don't just, you have multiple, like Gaia data, you would have like more than 100 columns for each star, right? And then you're trying to look for some kind of a pattern in that data which is there, right? So therefore you can, you basically, another thing is that since the data is so much, you basically need to train or teach computers how to sift through the data, right? And look for patterns, find connections and do it. So this whole process is what we call machine learning, where machines learn to actually explore the data, sift through the data, look for it and look for things which are meaningful. Now, artificial intelligence is the bigger block, right? That's what came in earliest, the very first. This came in the 1950s, 1970s, artificial intelligence. Then came in the 80s to 2000, 2010, came what is called machine learning, which we'll be talking about more today. And then from the 2010s, we have what is called deep learning. So we'll be covering some deep learning next week, okay? Next week, we have another session again with AI/ML thing. So next week we'll be doing more about deep learning. But this week we are going to stick to machine learning, right? So what are the things that machine learning does? So for example, machine learning can be what is called supervised, unsupervised reinforcement. Sir has already explained to it, but we again look at it. What do we mean by supervised? What is unsupervised? What's reinforcement? So supervised is what we use to actually predict next value. I'll show you what it means. Unsupervised is basically to identify clusters, data driven. Reinforcement is where you learn from your mistakes, okay? So you reinforce your understanding. So what is a supervised learning algorithm? For example, you could use it for two ways. For example, you could use it for classification. So classification is what, for example, I think sir mentioned to you, for example, dogs and cats, okay? You want to differentiate between dogs and cats. So what do? I show you 100 images of dogs. I show you 100 images of cats. And then when I show you an unknown image, you look for similarities and you come to the conclusion whether what I showed you is a dog or a cat, right? This can be, for example, classification of any kind, gender classification, anything. So your result in this is just classification. Yani you say whether this thing is here or it's there. That is what we call a classification problem. You just have binary, two things. The other thing which we often do is what is called regression. For example, we have points of data, and you, for example, when you do a straight line fit, right, you are actually doing a regression thing. What are you doing by regression? Because I do this straight line fit. If I don't even have a point up here, because I know this straight line fit, I can use it to predict a value over here, right? So you could use it to actually predict continuous values for various things, right? So supervised learning, what happens is you have what is called labeled data. I have labeled data of these are dogs, these are cats, so that then I can say whether the thing is right or wrong, okay? For example, one example of this is what is called the galaxy classification. Now, you know, galaxies could have various morphological types. They could be elliptical, spirals, various kind of galaxies. So therefore, there are many surveys of galaxies where we have millions of images of galaxies. So it's obviously not humanly possible for astronomers to be classifying it. Basically, because the number of astronomers is not in the millions, right? So what happens is there are what are called citizen science projects. Citizen science projects are projects in which people can participate if they are not astronomers. Even if they're not astronomers, then as normal citizens, they can participate in these things. And these also play a very important role in astronomy. So for example, here I show you an image and I ask you what is this kind of galaxy you're seeing in the image, right? So the galaxy could be a spiral galaxy, it can be an elliptical galaxy. So you train the observer, I train the citizen scientist to identify what is a spiral galaxy, what's an elliptical galaxy, what's an irregular galaxy. And then after I train the citizen scientist actually classifies it, right? But what is done in citizen science, because we know that the people doing it are not experts, right? The same sample is shown to more than one person. So for example, I have this galaxy where I say 8 people have classified it as spiral, but 2 have classified it as elliptical, right? So there is a chance of there being a mistake in the classification, right? So you may actually look for it, you may put a cutoff that I will take the galaxy morphology type. If more than 80%, for example, have classified it a certain type, then that is the type I will take. So what you are doing is you are giving some space for errors by people, and then you actually use that to classify. Fine. Once you classify this, right, we are talking about millions of galaxies, right? So you build up your data set. What is the advantage of building up your data set? That then when you're doing supervised learning, when I'm showing the machine different kinds of spiral galaxies, the larger my sample, the bigger the variety of galaxies I can show, and the higher the probability that when there's an unknown galaxy, the machine can correctly identify. Okay. Now these methods are very, very good. Why? Because for example, in supervised techniques, often what we do is we actually do a validation process. What do I mean by validation? That means that supposing I've already got the morphological types of 100 galaxies. Okay. I know the morphological types of 100 galaxies. Okay. Which I'm relatively sure about. Let's say because that's a smaller sample, I can verify it, I can be confident about it. Now what do? I train the system only with 70 galaxies, okay, not 100. I train the system only with 70. The system doesn't see 30 galaxies. And then when I'm testing it out with other unknown images, I add my 30 images also there. Okay. And then I can check that for my 30 images, which I supplied to the system, for which I knew the morphological type, how well does the system identify, right? So for example, if I know it does it for 28 out of 30, right? So then I can say that my level of precision in getting the morphological type is 28 out of 30. That means 2 out of 30 times I could have an error, right? Which is something like a 6% error. So that's fine. The important thing is whenever you make a measurement is to know the error in your measurement, right? So if I've classified even 1,000,000 galaxies, I know my error is only 6%. Then when I make some statements about those galaxies, which I've identified this thing, I can always estimate my error in certain quantities, right? So that I can do it correctly. So that's the big advantage of supervised machine learning techniques, that you can do validation, right? You can validate the results you get because you use a certain fraction for training and then you use another fraction for validation. So you check how well does your system retrieve what you wanted, right? The other thing that people use it for is also called variable stars. So we know there are many stars which are variable stars. That means their brightness varies in many ways. Now the brightness could vary could be because of intrinsic things. For example, the star itself varies. For simple thing is you have pulsating stars, Cepheids, RR-Lyrae. These are stars which actually expand, contract. They are pulsating stars. And because of that, they pulsate, okay? And their pulsations, their variations have a signature kind of variation, which we call templates, okay? So there's a fixed way in which you know the star will vary in terms of time, in terms of the difference in magnitude it will have, how bright, how faint will it go, what will you do, right? You could also have a variable star which is extrinsic. That means it's variable not because of anything's happening to the star, but for example, the star has an exoplanet, okay? So it could have a planet in front of it. It could be part of an eclipsing binary. That means there are two stars which are, causing the variation, various things which could do it. So what is done is that templates are built which characterize the light curves of these stars, right? And once you have these templates which characterize the light curves, if you have an unknown star, okay, I show the system an unknown star for which I do not know what kind of a variable star it is, I can match it to the templates to check as to what is the variable type, right? And so that's how it's done with variable stars. Again, the problem is that because you have a billion, for example, in Gaia, you have a billion stars, right? So in these billion stars, how are you going to identify what is the variable type, right? So it obviously works out if you have these templates. With these templates, you can very easily identify what is the variable type. And then once you know the variable type, you can say whatever it is, right? So that is the thing with this. For example, here, this is transit light curve, supposing that if you have data of exoplanets, right? You know the different kinds of light curves you get with different exoplanets, right? And therefore you can actually, again, fit it to a template and figure out what is the exoplanet like. For example, these are very clean data sets because this is a single exoplanet going around a star. But for example, if you have 4 of them, 5 of them with different time periods, obviously your light curve is not going to look so neat and nice like this one does, right? So you will need to change it. People could also use it for redshifts. For example, I have spectra of galaxies and I'm using this to find out the redshift to a galaxy or the distance to a galaxy. So that could be with the redshift. The three-body problem is a classic mathematical problem, okay? Why? Because for two bodies we can solve it, but for 3 bodies it becomes highly chaotic and unpredictable. It has no analytical solution except for a few special cases. And therefore you can solve the equations only numerically on a computer, right? But even when you're doing it numerically on the computer, it's difficult because it's very sensitive to initial conditions. So what was done is using machine learning. We don't have the time to talk about, but you can actually Google it and read about it, how they actually kind of solved the 3-body problem using machine learning. Okay. So various things have been done with this. This is the image all of you all are aware of, which is the imaging of black hole, Event Horizon Telescope. And basically the image, again, we don't have time to go into the details, but in imaging the black hole, they actually used what are called CNN, convolution neural networks. This is a technique of deep learning, which we will discuss next week. And you will say that in constructing this image, they actually used computational imaging algorithms, which are based on deep learning. Okay. Now, in my case, let me go on to my case, the one that I was studying, and that is the case with star clusters, because I basically work on star clusters, galaxies, etc. So we know that stars are basically formed in groups, right? So 70 to 90% of stars form in an embedded cluster. Some of them remain bound, evolve as open clusters. The remain, they disperse and contribute to the galactic field. So multiplicity is the norm. But star clusters, if you see pictures like this, right, they are not static, okay? They're actually dynamic images in the sense, when you're looking at each of these stars over here, this is just a snapshot. But actually the star is actually in motion. And these guys have really high velocities. They could be up to 100 kilometers per second. They could have various kind of velocities. These are large velocities, okay? Not small velocities that these stars have. So star clusters are important because, like I said, stars are born in groups, and these are basically star clusters. And these star clusters are the building blocks of galaxies, right? Galaxies are basically made up of stars and gas, etc. So what happens is, if you want to understand the formation and evolution of galaxies, you obviously need to understand at the level of star clusters. Okay. So what I said is from a telescope called Gaia. Gaia is a space telescope which was launched by ESA, which is the European Space Agency. The advantage of this telescope is it is sent out in space. This one is in space. And therefore, we know that because of the Earth's atmosphere, you do have, movement of stars, right? They kind of move, which is what we call twinkling, right? And therefore, and because of turbulence in the atmosphere, various other factors, you do not very accurately pinpoint the position of a star. It shifts, right? And therefore, if you send out your telescope in space, the accuracy with which you can measure its position is really very high, okay? And this will be diffraction limited, right? So what happens is, in this case, is this telescope is sitting at the L2 point, the Lagrange point 2, in the Sun-Earth system. So you know that the Sun-Earth system has 5 Lagrange points. The Lagrange point 2 is the one behind the Earth. So it's ideal if you're not looking at the sun, for example. So this is the Lagrange point 1, 2, 3, 4, 5. So this is where Gaia sits, which is L2. Also James Webb sits over here, Planck sits over here. These are all telescopes which are a solar telescope. For example, ISRO Aditya L1 sits at L1. So if you want to observe the sun, you should put your telescope at L1. L1 will always look at the sun. But if you don't want to look at the sun, you will actually go on to the L2 point, right? So Gaia is sitting at L2. This is what the telescope looks like. It's basically made up of 2 mirrors. And what it basically does is it measures the parallax. What is the parallax? The shift in the position of a star, right? With your baseline. So we actually do that with our eyes, but here you are doing it with 2 mirrors. Okay. We also, because it accurately measures the position of stars, it also can accurately measure the velocity of stars. So what do we get? We get what is called radial velocity. Radial velocity is the velocity in the line of sight, which we'll get from Doppler effect spectroscopic data. Okay, this is radial velocity. This is along the line of sight. And then along this, in the plane of the sky, we resolve we have what we call the tangential velocity. Okay, the tangential velocity. Now this tangential velocity, we actually measured it in what is called the proper motion angle. Okay, so the proper motion angle is measured in proper motion RA, proper motion dec. We resolve it in both coordinates. Now, what is the method of parallax? Parallax means, for example, if you're the Earth going around the sun, you look at a star today, you see the angle here. After 6 months, when you reach here, you see the angle here. Half this angle is called the parallax angle. If this is what we call 1 astronomical unit, then distance, this is the angle, parallax angle, opposite by hypotenuse, which is 1 divided by d. So parallax is 1 divided by d, where this is in units of astronomical units. So you can, if you can measure this angle correctly, you know this distance, we can actually find out the distance to a star, right? So now what happens is, So you actually look at a star, for example, 6 months from now, it's over here. After 6 months, it's here. You're seeing that there's a shift in the position. It's moved from here to here. Okay. So basically, this whole story comes because you can accurately measure the position of a star. Because you can accurately measure the position of a star, you can measure its velocity also. Why? Because you know its position today, you know its position after 6 months, and you can find out that shift. Okay. Now let's look at the star cluster. This is a star cluster. You can see a whole bunch of stars, red and blue and white and various colors. The biggest question is, which of these stars belong to the cluster? Okay, membership. How do you know membership of these? Because if this is your cluster, you could have stars in the foreground, you could have stars in the background. How do you know which ones are the members? Now, there are various methods of doing it through what is called photometry, kinematics, spectroscopic, various methods to do it. But what we do with Gaia is you can actually use the concept. We know the positions, so we know where the stars are. We know their distances. So if it's part of a star cluster, they should be at the same distance. And if they are in a cluster, they should all move with the same velocity, right? So the parallax should be the same, and proper motion RA, proper motion dec should be the same. Now we use machine learning techniques. We have actually, since for the students project, we used supervised as well as unsupervised techniques. So the first method we used was what was called random forest. What we basically did in random forest is that we took a sample of star clusters, okay, 9 clusters, for which we had ages, the whole range of age, 1.3 to 20 million years, all at a range of galactocentric distance, that means distance from the galactic center, and various galactic latitudes. And what we did is we actually found out members using a technique called random forest. I think it was, Sir spoke to you about it. You've heard about the technique. So what we did is we actually want to look for these groups of stars which belong together. If you see that this work was done earlier by another author called Cantet Gordon. This was done in 2018 with an earlier version of Gaia, which is the data release 2. We have worked with data release 3. Oh, sorry, this paper is also data release 2 only. But what we did is these guys did it only till magnitude 18th magnitude. We have done it for a deeper magnitude. And therefore, if you see that for our 9 clusters, the orange stars are the ones identified by those authors. Blue ones are now identified by us. So the number of stars we've identified are much larger. If you see the distribution in parallax, that is the distance, orange was done by those authors, blue are our new members, and green is the total. So you can see the green overlaps well with the orange, which shows us that now our new sample is very similar to what was found earlier by these people. We also found structures in velocity space, which are shown here, and we plotted the color magnitude diagrams now with revised membership of these star clusters. So the orange ones were the old ones and the blue ones were the new ones. You can see that the number of members we've got is much, much larger after we did our random forest. We also, like I told you about validation, we had methods to validate our membership, and you can see that our membership essentially is 90% almost, though we even have something at 86. But you see the other ones we have is 94, 93, 92. So we have a pretty good value of it. We have almost double the number of members, triple the number of members, and hence got much interesting data with random forest. So we increased our members by 2-3 times. We see structures in velocity space, revised the sizes, and this was the work which we did with random forest. Now, the one problem in supervised learning is, like I said, you have labeled data. That means you have stars which are members. And obviously, your results depend upon how well did you identify that. We did it fine because we used these orange stars which we had, which was identified by those previous authors as members. We used them for supervised learning, right, to say that these are members. And then we use that for validation also. But if supposing you don't trust your supervised set, you don't trust it, then you may want to use unsupervised methods, right? That means you are not assuming anybody to be a member. You don't want to assume anything. And therefore, we used what are called unsupervised learning techniques. And the standard one which is used in this case is what are called clustering techniques. So if you have a 5-dimensional space made up of RA dec, parallax, proper motion RA, proper motion dec, then in that case, you can actually have cluster members will literally cluster in that 5-dimensional space, right? So there are different kinds of clustering algorithms which are being used, and we basically use two different algorithms. I won't go into these details, but we used one which was called Gaussian mixture modeling and another method which was called DB-scan. Now let us see what is Gaussian mixture modeling and then see what is DB-scan. So what is Gaussian mixture modeling? Let's say we have two clusters over here, these two clusters, the blue and the red. If I were to plot the distribution, this is the blue and this is the red. When I see it combined, I will see the green, right? So what you do is you break up, if you observe the green, you break it up into two Gaussians, okay? Saying that both of these will be Gaussian, so you break it up into two Gaussians. One Gaussian will be, so ideally if these are nice clusters, that if this is A is the size of the cluster, B is the distance between two clusters, okay? So if they've been nicely separated, then if I were to take B minus A, maximum between A and B would be B, and if A is very small comparatively, my S would be approximately 1, right? The silhouette score. So, but we defined something called the modified silhouette score, defined by the standard deviation, okay? So what do we know? That the Gaussian for the cluster members will be narrow, right? That means the standard deviation will be small, okay? But for the field stars, it will be very wide, because field stars will have a total range in parallax or in proper motion RA, proper motion dec. So we instead of doing this silhouette score, which is B minus A, we actually defined it as sigma of field minus sigma of member with the maximum. Again, if you have a good separation, your modified silhouette score will again be 1, like silhouette score was also 1. So if we use GMM in open cluster membership, we use this technique. In Python, if you were told about scikit-learn, right? Scikit-learn actually, what do you say? In scikit-learn, there is a package for GMM, and that's what you can use if you want to actually, do this thing. So if you want to run, okay. Yeah, okay. I'll just answer your questions a little later. I can see their questions, but I'll just answer them a little later. Okay. So in scikit-learn itself, there's a package for GMM. So look at this over here. The cluster stars are the red ones and the field stars are the blue ones. So the cluster ones are nicely peaking at a narrow value for parallax, proper motion, or proper dec, and the field stars are wider, standard deviation wider. So this is one of our best results, which is with M67. And with M67, we got this. This was where the cluster was. And these are our things. And this is my clean color magnitude diagram. Okay. So that's what we did with GMM. Again, we did it for a set of 9 clusters. That's our set over here. Some of them overlap with the random forest, some don't. So we have a slightly different, or we did more, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So for 13 clusters, we did it. Okay. Now, in this case, in unsupervised method, we do not have a method of validation. Remember, I told you in supervised, you can do the 70-30 break and you can look for validation, right? In this case, we do not have that pleasure. And therefore, what we actually did is we used spectroscopic data, okay? That means if stars belong to a cluster, they should have the same chemical elements also in them, right? That means their spectroscopy should be similar. So there are some spectroscopic surveys, like there's ones called Apogee and Gala. So what we did is that we used these 2 surveys to actually look for so what you see on top is the one which was the training set which we had used, which was giving us the chemical composition of that. And this is the chemical composition of our members. You can see it almost is identical up and down. That means the chemical composition of our members is exactly the same like it was for the training set, implying that most probably the members we identified were all good, were all nice. We also use the membership list to actually get cluster parameters. So there is a software called Azteca. Some of you all, if you all do the capstone project with star clusters, you can use this software called Azteca, for which you can use Gaia data, and it will help you to find out all the parameters for a star cluster. For example, its distance, its age, its members, its various parameters, right? So you can see here are all the parameters given for this cluster, based on the membership data which we got from GMM. Okay. So this paper was also published separately. Now we did another one where we actually tried to use it using a method called dbScan. What does dbScan do? dbScan is a method. For example, look at this set of stars. For a given star, I draw an epsilon radius, and I check whether the star has a minimum number of points, supposing 4 points in that epsilon radius. So for each star, I draw a circle with epsilon radius and check whether, say, it has minimum points 4. This star, for example, I draw epsilon radius. This one has 4 stars. So this one is what I call a core point. This one, I draw this over here, but it does not have 4 points. So therefore, this is what is called a border point. This point, for example, I draw an epsilon radius. I don't find any stars in it. So this is what we call a noise point. So every point gets identified either to be a core point or a border point or a noise point, right? So based on this, you identify your clusters. So you join these together and you use this to identify what are called clusters. This is called the dbScan, density-based spatial clustering. So again, with the same clustering, remember I showed you for the GMM, we also did for M67. This is how we got our things. You see, remember I told you the earlier sample has only till 18th magnitude, and therefore these orange stars are only till 18th. We extended it further here and got it till 20th magnitude. And these are the new stars which we got. And we used Azteca to get this thing. Again, to validate it, we used Apogee Gala survey to actually see that the spectroscopic details are the same for all these stars. Again, we can use Azteca, get the parameters for it. And we got the result for all our stars with dbScan. We also use machine learning to study a star-forming region, which is Serpens. What we did in this thing was slightly different. We actually used available VISO, Young Stellar Object Catalogs, to identify VISOs in this region, right? Now what we did is we got this VISO sample, we matched that with Gaia. This is what is called the EDR3 data, early data release. This is before DR3 came. We get the parameters for the stars using EDR3 data. Then we use that to make a control sample, query EDR3 data in 2-degree radius for this thing. Then we used ML techniques, dbScan, optics, and HDBScan to identify members, and then look at their parameters. And if you cross-match VISOs with TUMAS and WISE, you can also get their classes. What is their type? So this was done for Serpens. This has been done also by Herzeg et al. 2019. He did it for this large region. We did it for a smaller region. This is our sample, our control sample, which is 87 stars, for which we have the distance, the proper motion array, proper motion deck. We have all the values. We use this to query the EDR3 data. I won't go into detail. These are the details about Gaia data, the Rouve index, etc. Once we got all our data within a certain range of parallax, proper motion array, proper motion deck. See now, what is it basically doing? Think of these clusters like islands, okay? You have water, okay? Now, depending upon the depth of water, the amount of islands you see will vary, right? When we do dbScan, the depth we take is a fixed depth, okay? So using that, you get a certain distance. If we use a method called HDBScan, HDBScan is hierarchical dbScan, then the level of water varies at different points, okay? So you may be able to access more islands or more clusters compared in dbScan. In dbScan, everybody has the same epsilon value, right? But in HDBScan, it will vary. So for example, if you're studying a star cluster which has a small size, say 10 arc minutes, then dbScan is good enough because the density is about the same. But if we are doing star-forming regions, like now, I'm not talking about that today, but I'll talk about that some other time. We are studying Perseus. We are literally taking a 30-degree field. So then what happens is the number of stars varies a lot. So then you need to vary this height, right? And then we use this technique called HDBScan. So dbScan I already explained to you. HDBScan is variable, and there's another method called optics, which will vary the depth. This is varying the depth. If I keep the depth so much, I get 3 clusters. If I keep the depth here, I will get these and these. So I need to know how to vary the depth so that I get maximum number of clusters. This is using a method called optics. HDBScan varies the depth, and therefore for this method, we actually used HDBScan. We compared our results from all the different methods, and we used this to identify our clusters. And we got basically these 2 clusters, and we plotted them on our diagrams. We also, this is on the CMD, we plotted them. We also used WISE and TUMAS data to identify the the classes, class 1, class 2, class 3, what kind of ISOs they are. We plotted them also and studied various things about them. So that's what we did with that. So I will now wind up that here we've used three different techniques of machine learning: random forest, Gaussian mixture modeling, DB-scan, HDB-scan, specifically for this case with Gaia data. Obviously, you can use it for other things, but this is the one we did, and that's why I spoke about it. If you see, you need to pay attention to the algorithms you are using, what are the errors you are getting, and those are all issues which need to be considered. So I'll end with this, and I'll just take your questions fast. So I can see, what's the time?
11:10.
Okay, very good. So Emmanuel asked me, was the cross matching of YSO, infrared and EDR3 done with EO? Yes. It is, Emmanuel, it's always good to do the cross matching with VO tools. Why? Because VO tools are a little smarter. For example, if you were to just cross match a star with its closest match, right? The closest match need not be the correct match. Okay, you'll see, if you see 2MAS, where you have like 100 stars in this thing, you may have 1,000 stars in 2MAS, right? It depends upon the region you're studying, obviously. But obviously, it is very possible that your closest match is not the right match, okay? So if you just use, if you don't use VO techniques, right, you may just take the closest match as the right match, which is obviously not the right match. So even cross-matching is a whole science as to how do you cross-match. VO tools do it a little bit more smartly. And therefore, for example, Gaia, within Gaia itself, you can ask Gaia to cross-match. So actually, that's what I did. I trusted Gaia to do the cross-matching and not myself. Because if I do it myself, I will do it as the closest match. I don't want to do the closest match because the closest match is not necessarily the correct match, right? So Emmanuel, you need to be very careful while doing, basically because the resolution of Gaia is different, of 2MAS is bad, okay? The thing is bad. And for WISE, it's even worse, okay? For WISE, it's even worse. So you need to be very careful, especially when you are cross-matching across wavelengths, because the kind of, it doesn't actually sit, okay? The kind of resolution you have in different wavelengths is different. And like I told you, the other important point is the closest match need not be the right match, okay? So Emmanuel, you need to be careful about that. Okay, Prachi, I'll share the PPT. This was actually not planned, but I'll share it, no problem. Nathan, with what matters, how biased is unsupervised learning? Because if the machine doesn't have our mind of thinking, our minds still, okay. So Nathan, like I told you, supervised learning works very well if you are very sure of your labels. You understand? For example, the 100 images I'm showing of dogs, I need to be 100% sure that these are real dogs, right? But often what happens in astronomy, right, in real world, we are not always very confident of our labels, right? If we label a thing as a dog or a cat or whatever it is, right? Or as a member or not a member, like in this case, we may not be too sure. You would be sure to a certain probability, right? So that means for membership also, we always calculate what are called probabilities. This is 95% a member, 60% a member, 80% a member. You are never 100% sure. So if you are not 100% sure, when you are using your supervised set, you need not be so confident, right? So then if your training set is not with full confidence and the results which you get with a not sure training set need not be good, right? Unsupervised, obviously, you're not taking a training set. So you have lesser things to fall back to. So, but it, like I'm saying, it's a trade-off. Either you take things you trust, or if you say that you don't trust it, then better don't trust anything and do it without that trust, right? So that's why I'm saying, that's why when we worked on it, we worked with all options for supervised as well as unsupervised. Our supervised came out pretty well because the supervised set which we had was a good set, right? And therefore it worked out fine. But one needs to probably test it out, that supposing if you have different degrees of contamination in your training set, 10%, 20%, 30%, then how does it work? right? Then it need not work so well. In ours, it worked well because our training set was good. But so it's basically it's a choice of what you have, right? Do you really have good labels to your data or you don't? So based on that, you decide what to do. So you have to just live with what you have. Yeah, okay, I'll put this on the GitHub repo. I'll put that. Okay. 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 Yeah, Harrison, you've asked me how to download data from Vizier. Okay, I'll do that. I can stop share. So you basically need to open your Chrome, right? I hope you all can all see my Chrome. Oh God, I don't want to show you all this one. I'll show you all this one. Okay. Can you see my Chrome now? Najam, can you see my Chrome?
Yeah.
Can you see my Chrome?
Yeah,
Yeah.
yeah.
Okay, very good. So all you need to do is you will say Vizier. Okay, you will type Vizier, for example, and let us look at Gaia itself. You will say Gaia DR3, right? So here, what is it doing? You are seeing you're going to look for Vizier Gaia DR3, right? So you actually go into this, and we are going to look at Gaia DR3 data. This is Vizier, okay? So here you will see this. You'll come here and you go to CDS. CDS is the center in Strasbourg, which is the center for data. Okay, in French it is centered on this thing, but this is the thing. You click over here on Vizier. Okay, so typically here we are looking for Gaia DR3 data. We have Googled it. So if you know the author of the paper for which you're looking for, you will give that and you will hopefully get it over here. Now you can see this data set. There are different tables. This one is masses derived from non-single stars. This is Gaia DR3, source catalog for carbon stars. This is this thing. This is what? These are all different catalogs of Gaia. 1 minute, but I think this is not the one that we want. This is performance verification data. So this is not exactly what we want. I will just redo it again. Gaia DR3. Okay, so this is summary of the content. Okay, I'll go here. Let me go from here.
Search tables.
Okay, we can even do this. You can go directly to Vizier, right? Here, this is Center Strasbourg. You can do, there are many ways of doing the same thing. You may over here look and you may write, I may say Gaia, okay? And I say find. If you have the author of your paper or whatever, you can give it. Now you can see this is Gaia DR1, Gaia DR2, EDR3. This is Gaia DR3. This is the main source catalog. There are other catalogs, for example, for extragalactic sources, non-single stars, variability, all these different ones are there. Let's say you're going in for this. This is the main catalog, which is 355, which is the main source catalog, okay? Now over here, let's go in for this. This is Gaia DR3. Okay, here you click on this. Now here's your source. So what you need to do is here, for example, you can even give a source name. For example, I'll give NGC 581 and I can give a size of 2 arc minutes. You have to actually here click. These are all the available columns. The default ones are clicked, but you can actually add in whatever you want. You can also put conditions. For example, I can put a condition, parallax greater than 0. Okay, you'll see that the way the system runs, you even have negative parallax, which actually doesn't make sense, but it's part of the data processing. So you say, okay, I want parallax. You can put your conditions over here. You can submit it, right? And you'll get your result over here. Okay, this is an HTML table. Here you have choices. You can actually put it. What is the maximum number of sources? You can say unlimited. And here there are different, formats in which you can download it. This is a VO table format. This is the FITS format. The CSV format, tab separated variables, this is CSV, or whatever kind of format you can choose. So for example, I may choose a VO table format, unlimited thing, and then I may query it again. So I may take this and I'll say submit. So I'm submitting it. And now instead it's going to let me download. So now it's letting me download my data is this. And that's what I will do. So essentially, that's how you basically download through Vizier. Vizier, basically, it has a lot of data sets. It also has the data that people have used in publishing papers. So even that data is available. So you can find it through Vizier, and I hope that helps. So that will help you for your capstone project. You will find data using these methods. Okay. So I'll end over here. Let me see if there's any other question. What happened?
5 minutes, I'll just show one. I've shared one file.
Okay, just, yeah. Audio, you need this audio.
Yeah, hello. I've shared one Jupyter notebook, and this is with the Gaia data doing. I'll just. I hope you can see this here. So I have shared this with you in the chat window. I've shared the presentation I showed and the other two Jupyter notebooks, and here's one where you will see that we can do these machine learning things using the Gaia data. Okay, so you can run them through, and there are some good habits before modeling and clustering, finding groups, and you just read through this. And how do you do the cross validation, some comments. And basically, this is going to look at Gaia DR3 data of cluster membership of a certain object, and this will show you how to do that. So in the first one, you are importing all the required, setting up the environment, import NumPy, pandas, this, that, scikit-learn, and so on. And we'll be doing dbScan here. So we'll be using k-means and dbScan here. This is added here. And from pathlib, import path, and you will download some small Gaia DR3 table. Right, so it selects a source with 1 degree of M67 with basic astrometric and photometric quality cuts, and the result is cached locally as a comma separated variable file. So I've sent that file also. Somebody was having a problem downloading it. So this gets locally cached, and here it is. So you specify how many you want, which are the source. You need source ID, RA, DEC, parallax error, whatever you require. You query with that. So these are the typical SQL commands, very simple to understand and so on. So you sort top 7,000. You can look for 1,000 or whatever, right? And what all you require, the source ID, RA, DEC, parallax error, PMRA, PMDEC, PM error, and all this, RUWE, and so on. And you can download it, and we are seeing that file. So this has 5,387 rows, and we are building features for clustering. Exactly as we made a copy of that in Gaia M67, and we are getting it into a format which we require. And we are running the dbScan here. We are using this pipeline scalars. This is rescaling the thing and running dbScan with epsilon 0.35 and mean sample size here. To go through this, in our next sessions, we will be discussing this in detail, what is dbScan and what is AGBScan and so on. But as a preliminary one, I have shared it with you, and we can plot, you can plotting it in PMRA, PMDEC space, and you are getting the members here, right? The ones which you have in the header. the color magnitude diagram. The ones are the whole data set, all the row tables, but after you sift out the members of the cluster, these are the cluster members, and right, so you can go through this Jupyter notebook, and when we meet again, you can discuss this. So maybe with this we should end for today. And yeah. Okay. Okay, so yeah, shall we stop for today?
Yes, of course we can. You guys are done, and I think it's almost time for it's almost 2 hours into the call. And then thank you very much, Najaman Priya, for the wonderful presentation. Please, to the participants, you need to take the lecture material seriously. Remember to run through the notebooks, read them extensively, and follow the examples. So thank you very much. We'll convene next week, Wednesday, to continue the second section of machine learning. Leo Priya and Najem will also provide extensive knowledge on concept of the other aspect of machine learning and deep learning. Thank you very much. Do enjoy your week and enjoy the rest of your evening. Bye.
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 Hearts.